Welcome to Relativity. This is review lecture 26a. Upon successful completion of this unit, you should be able to understand Galilean and Einsteinian relativity, understand the equivalence principle, understand special relativity, solve problems in relativistic velocities, time dilation, and length contraction, solve problems in relativistic momentum and energy. If we do get that far, maybe understand a little bit of general relativity. We probably won't get that far. Einstein lived from 1879 to 1955, and he was one of the most influential thinkers in history. Probably more people have heard of Einstein than any other scientist in history. Einstein's first paper on special relativity came out in 1905 and dealt exclusively with inertial reference frames. 10 years later, Einstein published a more encompassing theory of general relativity that considered accelerated motion and its connection to gravity. Now, this figure shows two reference frames called S and S prime. The coordinate axis in S are X, Y, and Z, and of course, Z is coming at you out of the page. We're not showing you that. The coordinate axis in S prime are also X prime, Y prime, and Z prime, and of course, Z prime is coming out of the page, so we're not showing you that. Frame S prime moves with velocity v, a constant velocity v, relative to frame S. So that means, equivalently, frame S moves with a constant relative velocity v minus, or minus v, relative to S prime. There are no such thing as a preferred inertial reference frame. So these, we just mentioned before, frame S moves with velocity minus v relative to S prime. S and S prime are both inertial reference frames, implying that the relative velocity is constant. There's no acceleration here. So an inertial reference frame is a reference frame in which Newton's first law, the law of inertia, is valid. In other words, there's no acceleration. Which is an inertial reference frame, or at least a very good approximation of one? Well, it's the one that has no acceleration. Obviously, that knocks out A and C, so the correct answer to that one is B. A jet plane flying straight in a level of constant speed. An inertial reference frame cannot accelerate. Okay, now this is the Galilean transformations. Suppose we have a firecracker exploding at time t. In reference frame S, this explosion happened at position X. In reference frame S prime, the same explosion happened at position X prime. So here's X prime and here's X. We can relate these positions with transformations. Now, it's important to note that the origins coincide at time t equals 0. So we're going to consider these two reference frames at S and S prime. S prime moves at speed v relative to S in the minus X direction. The origins of S and S prime coincide at time t equals 0. At time t, an event happens in coordinates x, y, and z and S, and x prime, y prime, z prime, and S prime. These coordinates are related by the Galilean transformations of position. X equals x prime plus vt. Of course, y equals y prime and z equals z prime. Now we can turn this around just by doing this algebraically or by inspecting the diagram up here. X prime will equal x minus vt. Y prime equals y and z prime equals z. The velocity v is in the xx prime direction. So only the xx prime directions are affected. The y and z prime directions are not. In reference frame S, an object moves with velocity u. Okay, so that's in reference to this reference frame here. In reference frame S prime, the same object moves with velocity u prime. Now notice, the only thing that's different here is the x coordinate. The y coordinate is not changed because there's no motion, relative motion in y and y prime. The only relative motion is v in xx prime. That's the reason the direction is different. Now we're going to consider these two reference frames again. Again, S prime moves its speed v relative to S in the positive x direction. An object has velocity components ux, uy, uz in S, and u prime x, uy prime, uz prime, and S prime. These velocity components are related by the Galilean transformations of velocity. Ux equals ux prime plus v, uy equals uy prime, uz equals uz prime. Or, just turning this around, ux prime equals ux plus v, uy prime equals uy, uz prime equals uz. Now notice the only things that are different here is the xx prime direction because v is entirely in the xx prime direction. Now we're going to have a force here and acceleration. Of course, the S prime coordinate system, remember, is moving at velocity v with respect to the S coordinate system. So the force on an object is the same as measured in two inertial reference frames because they're inertial frames. The acceleration of the object is also the same in both frames. A equals A prime. So this says that but this is the Galilean principle of relativity. The laws of mechanics are the same in all inertial reference frames. So that means there's no preferred inertial reference frame. That's because V is constant here. What I mean to say is there's no acceleration of one frame relative to another. So in other words, the acceleration of anything in this frame is going to be the same as anything in that frame. Okay, balls 1 and 2 are about to collide. Here's balls 1 and 2, and here's the S frame, and here's the S prime frame. And remember that S prime is moving at velocity V with respect to S. What is the velocity of U prime 1I of ball 1 in frame S prime? Well, it's going to be equal to 6 meters per second. You take the 2 meters per second of ball 1 in the S coordinate system and subtract from that minus this right here. You can sort of see what's going on here. And what you're looking at is basically this one is moving relative to this, but this frame is slamming into this ball. So look at this from here. Pretend you're standing on this frame and look back at this ball. You can see that these two velocities are going to add. So this frame is kind of slamming into that one. Ball 1 and 2 about to collide, have the velocities as shown in reference frame S. What's the velocity U2I prime of ball 2 in frame S prime? It ends up being 0. So what you're looking for is this one right here is moving along with this frame. So relative to this frame, this is not moving at all. Thank you.